Okay, hello everyone. Hope you are doing well. Welcome to week six. It's the fire safety in construction part two. Actually, I delivered the lecture for the week five regarding the fire safety in construction part one. At the beginning, could you please just confirm that you can hear my voice clearly and also you can see my screen?
Yes, audible.
Okay, thank you, Vedal. Thank you so much. So yeah, let's get started. So this week, like the previous lecture, so I'm gonna just divide our session in two parts. The first part is about the theoretical, the last part, and also the second part is about the practical and training the FDS and some simulations. Okay. So as I introduce the references, so I am use these four references for preparing these lecture notes: the fire safety engineering design of structures, principles of the fire risk assessment in building, handbook of the fire and explosion protection engineering principle for oil, gas, chemical, and related facilities, and also the Australian standard 8051 routine service of fire protection system and equipment. So from previous session, if you have any question, please let me know. And also, if you were absent, so I can just quickly remind you what exactly we discussed. So let me just check our chat box. Okay, thank you so much. Thank you, Sam. So very quickly, I'm gonna just reminding you. So we have the different classes of the fire: class A, class B, class C, and the class D that you can see the details. And I don't want to take a lot of time for the reminding. So then we just talk about the fire growth. We have actually four different stages for the fire growth. Stage one is means that's the initial stage, and we can just flash over or the fully developed fire. And also the last one is the decay or the cooling period. And then we discuss about the fire spread internally or externally. Then I gave you some precautionary measures that we have to take them actually in construction in our building. And then we discuss for the activity, and after the activity, I explained that we have three different detectors: the heat detectors, smoke detectors, and the flame detectors. I'm pretty sure that you are familiar with these two. I mean that the heat detector and actually smoke detector, but the flame detector generally used in boilers and in industry. So based on the Australian standard 8051, so we have a routine service schedules and we have to follow the instruction regarding the frequency and regarding the procedure. And then based on the different classes of fire, we can just select and choose the appropriate, the proper one, the proper extinguisher for our hazard area. For example, when we have for example, the wood or the paper, the fire is because of the wood and the paper. So we can use the water, but on the other hand, when we have, for example, flammable gas, so we can't use the water. So for example, we can use some powder. So we can just select them based on the class of fire that we estimate. And now it's time just to start our this week's actually session. So very quickly, I'm gonna just summarize the theoretical part and we can just work on simulations. Very quickly, we have a different sprinkler system. So the first one is the wet pipe system, and these systems are always filled with the water, and either for the buildings where the freezing is not an issue. Let me just explain that the structure of the sprinkler, I think, is familiar to all of you, and all of you actually have seen the sprinkler at your building, at your university, at the shopping center, and actually different places. So the structure of the sprinkler head is like this. We have a bulb, and this bulb is filled with liquid. And generally, the sprinkler head acts like a plug. And so when the temperature of the liquid increases because of the heat, so it starts breaking the bulb. And in this way, it means that we can have water, and we have the spray of water. So we can have a wet pipe system, or if we have no freezing issue. But if we have a freezing issue is our concern. So it means that we need just to replace that with a dry pipe system. This system filled with the air or the nitrogen. Water is released only when the sprinkler head is activated. It means that the bulb breaks, and so we can have the water. So the figure shows that the pipe connected to the sprinkler are filled with the air or nitrogen, and we have the water here. When we have the sprinkler head activated, so it means that we can have a water inside the sprinkler pipes. The other system is the deluge system. So the deluge system used for the actually high-rise building or industry. So sprinkler heads are open and connected to a water supply, and they are used for the high hazard areas. I think again this system is familiar to all of you, and you have seen that, for example, on the campus or close to the high-rise building. And the fourth one is that the pre-action system. So this system is a bit different because it requires a two-step activation process that minimizes the accidental discharge. It means that we have the two activation steps. The first activation, it means that we can have a water inside the sprinkler pipe. But when we have activated the sprinkler head, it means that it allows water to flow and just discharging from the sprinkler. So here there is a note, and it shows that the deluge system are filled with the unpressurized air and open sprinkler head, while the pre-action system are filled with the pressurized air, and each sprinkler head is activated individually depending on the location of the fire. So this system, I mean that the pre-action system are very efficient and effective for just preventing any false alarm. And also we have other different fire protection or the suppression system that you have seen them, and they are very simple. For example, the fire blanket, maybe you can see them on the wall. So they are effective way just for smothering the small fire or wrapping around a person whose clothes are on fire. So is this one. And also we have the fire hose reels, that this one that we have them are actually inside the wall, and definitely you have seen them. There is a red box. So this big system providing a continuous supply of the water suitable for the large fires. And also, as we discussed last week, we have the fire bucket. So this way is a simple and traditional, and is filled with the water or sand and used for the small fires. Maybe you have seen them in the servos, service station, fuel station, and some other areas. We have automatic fire suppression system. So this actually system actually dedicate the fire, detect the fire using the sensors and automatically discharge the suppression agent. I mean that this system. And also we have the gas-based suppression system. We can use two different gases. They are very clean gases, FM200 or Novec 1230. And they use just to suppress the fire and commonly used in the data centers and the server rooms. And the last one is the aerosol suppression system. So this system actually releases a fine mist of the chemical agent that disrupt the fire's chemical reactions. So if you remember, we have the different classes of fire. So for the chemical reaction, definitely we need this suppression system. And also regarding the other type of the fire suppression system, we have the water mist system. So it's more effective compared to the sprinkler, but it depends on the hazard area. So when we need that, so you can see that it's more efficient because it can just coverage larger areas, and actually you can control even the size and the angle of the water spray of the water. So use the fine water spray just to cool the flame and surrounding gases suitable for a variety of fire types. And the next one is the foam deluge system. I introduced the deluge system that actually this system were filled with the water, but when we have the foam deluge system, it means that for the case of fire, I mean that different classes of fire, that we need foam, so we can use this system. It's very popular and is widely used in industrial plants, such as, for example, chemical plants or power plants. So these systems distribute the foam through network of pipe commonly used in industrial setting and flammable liquid storage areas. And also the next one is the clean agent system. Again, we have these two agents. I mean that FM200 and Novec 1230. This system use these two friendly gases. They are very clean and they are suitable for protecting sensitive equipment. And the last one is the oxygen reduction system. So if you remember last week and even from your high school maybe, so you know that before the fire, we need three essential elements. We need oxygen, we need the heat, and we need the material. So I told you, if we can just remove one of them, it means that no fire occurs. So in this system, if we can just reduce, because the best portion, the best percentage of oxygen for fire is, as you can see here, is the 21 that is in the nature. But if we can just reduce the oxygen, so it means that when we reduce that, so we have incomplete fire, and as a result, we have a soot. But if we can just reduce that to, for example, 17%, it means that we don't have any fire, but we have to just consider different parameters such as the human and the breathing systems. Any questions so far? Okay, like the previous actually lecture, I consider one activity and it's like a fire risk assessment. So we need an evacuation plan for construction site. So this site actually is a large construction site, involves a multiple building under construction simultaneously. The site is complex with varying stages of the construction, different types of the material, heavy machinery, and a large workforce that you can see in the picture. So we need just to ensure the safety of the workers and managing coordinated evacuation in the case of fire. So you have 2 to 3 minutes just to think about that. And meantime, I'm here, just happy if you have any question. After 3 minutes, we can just discuss regarding the evacuation plan. So take your time. After 3 minutes, we can just discuss. If you are interested, so you can just unmute your mic and just engage in this activity, or even maybe you can just send your ideas through the chat box. Okay, so we have a message in the chat box. Yeah, investigate all sorts of the hazard. Yeah, thank you, Arma. And eliminate where the possible exactly and ensure that all the stuff are informed of. Yeah, and also equip for the hazard. That's fantastic. Battle is a conduct a fire drill. Exactly, we need just to do that. Yeah, yeah, good engagement. Yeah, we need just to make sure that all of the personnel, those personnel that I told you last week, some people, we need just to train them if we need. And just be mindful of this sentence because this site is complex and with the varying stage of construction. So it means that we need to consider, or it's better to say that we need just to adapt the actually our evacuation plan based on the different stage of the construction. So any other feedback, ideas, please share with me. Okay. So here you can see that we need to consider three main steps. The first one is just to develop an evacuation plan. So if there is no evacuation plan, so you need just to do that from scratch. So you need just to create a detailed layout of the construction site, highlighting all possible escape route, assembly points, and location of the fire safety equipment. And also you need to consider just to establish clear communication channel for the alerting workers about the fire, including the alarm, loudspeakers, and emergency contact procedure. We discussed them actually previously. So you need just to establish a communication system because when in the case of the fire, massive fire, maybe we don't have access to the mobile or the telephone. We need just to have an effective way for communication in the case of fire. And the second step is just to consider the different stages of construction. The point of this question was that it has actually varying stages. So you need just to adapt the evacuation plan for the different phases of project that acknowledge the route and safe zone may change as construction progresses. And also you need just to identify and mitigate risk associated with specific stages such as the use of flammable material during actually finishing stages or presence of welding activities. If you remember last week, I told you when we are just discussing the Barangoro construction site, actually the fire, so the final reason that was determined, it was the welding. So it's very important, and you need just to consider these potential risks and reasons in your plan. And also the last one is just strategies for safe exit routes and emergency response. So you need just to designate and clearly mark primary and secondary exit route, ensuring they are free from obstruction and easily accessible. And develop a response plan for different types of the fire, for example, electrical or the chemical, and train workers on the use of firefighting equipment available on site that you actually pointed out. And the last one is just coordinating with the local emergency service to ensure quick and efficient response times in the case of an accident. Yep. So any question on this activity or no? Okay, good. So I think it's enough, it's sufficient just for discussing some theoretical points. And it's time to just start our practical section. So I'm gonna just give you a very brief overview about the CFD and computational fluid dynamics. And after that, very quickly, I will just explain the FDS and we will run actually building, a fire in a building, and we can just discuss the different parameters. So when I use the CFD or computational fluid dynamics, previously I explained that we have different types of or methods for solving a physics in the real world. One of them was numerical simulation. So the computational fluid dynamics means that when we have the fluid, so we can just solve that physics through the CFD. So it's the knowledge just to solve the different problems. But the first step that you can see that different figures that we work in our group through the CFD. So the first step for the CFD is just to identify and understand the physics of your problem. When you understand the physics of your problem, it means that now you can select, okay, what are my governing equation in this problem? Definitely, as an expert, you can just select the governing equation of your problem based on your physics. For example, if you are simulating, let's say, for example, an aircraft or an airplane or a shuttle, anything. So you are just studying, for example, the behavior of flow, behavior of air around the wing. So aerodynamic. So you have, for example, the equation of the mass, conservation of the mass, or the momentum. Or if you want to consider the temperature, if the temperature is important, so you need just to include the energy equation. If you are just studying, for example, the behavior of the water, seawater around the, for example, the marine vessel or the submarines. So you need just only to consider the conservation of mass and also the momentum. It depends on your physics. So, for example, for a building that we have a fire, so it means that we have a conservation of mass. We need just to consider that. We have conservation of, for example, the momentum, energy, because we have the temperature, we have the different temperature, and also because we have a reaction, definitely. And also we have the species. It means that we have a reaction, so we can have the different species before the reaction and after the reaction. Just consider, for example, we have a methane. So in the reaction with the methane, in the case of fire, so we just generate the different new species. Even you can just, for example, use the CFD for the different and the wide range of applications. For example, the first one is just some fundamental or even industrial applications. Even you can just study the internal and external flows. I'm pretty sure that all of you have taken the fluid mechanics and you are familiar. And these couple of slides that I'm borrowing from your fluid mechanics unit. So it's just for reminding you regarding the importance of the CFD, and then we can just start our FDS software. So the internal or even external flow, when we say the internal flow, it means that, for example, flow inside and within the pipe, and the external flow, as I mentioned, the behavior of the structure over a ship, over a airplane. We can have CFD for solving reacting or non-reacting flows. So in case that we don't have any reaction, so we need just to use non-reactive flows. So again, you need just to understand and actually understand and determine that what is the physics of your problem. And based on that, just you need to consider different governing equation and analyze some initial primary analyzing your cases. And then depends on the physics of your problem, we can have the multi-phase flow. Sometimes you can just consider the single phase flow. It means that, for example, only you are studying the behavior of flow over an object, for example, a block body. So only you have water if you, or you have air. So it means that because you know that we have three different phases in nature, gas, liquid, and the solid. So it depends on your problem. You can just select your physics is multi-phase flow or just single phase. For example, let me just explain one of example from my PhD thesis. So I was studying the nanofluid for a project. So I had to consider just three-phase flow because I had the nanofluid. It means that I had the flow that is the base flow was water, and inside the water we consider and injected the very tiny solid particles, and then we injected the nanofluid as a mixture of the fluid, liquid, and the solid into the air. So at the same time, we had the air, liquid, and also the solid. So it depends on your problem. And also design process, or even you can see that we can use the CFD for the biomedical, aerospace, energy, and automotive. So here you can see that we use that for the upper airway or around the shuttle in the motor engines. So even for the wind turbine, so it has a wide application. So you can just use them based on your need. For if you are very interested in the CFD, so I'm just introducing five different references for the CFD. So the computational fluid dynamics, a practical approach, or the fundamentals of the computational fluid dynamics, verification and validation in computational science and engineering, and introduction to computational fluid dynamics, and the last one actually is written by Patankar, is the numerical heat transfer and fluid flow. So we have several references for the CFD, and they are not limited only to these five references. So if you are interested, so you can just uh, start to study one of these references. Very quickly, just talking about the process of the CFD, because you need an overview. So when we have a governing, the first step that is you as an expert, you should just select your governing equation based on the physics of your problem. And based on that, you need just to have some assumptions because you need just to simplify your problem. So you need just simplify your problem as much as you can. And after just simplifying the equation, so you need, if it's not possible just to obtain the exact solution that we discussed that, for example, you cannot just solve your equation through the analytical or the mathematical models. So you need just to use a numerical solution. They are very accurate, reliable enough, and they are very cost effective and stable methods. So all these process are named as the fluid mechanics, and this part, the last part, are named as the numerical methods. After the processing, so we have the result, and again, as an expert, you need just to analyze and evaluate your results. We can just divide the CFD problems in three different parts. The first part and the initial part is just pre-processing. It means that you need just to define your computational domain and geometry. So you need just to create and generate your actually computational domain, your geometry. You can use through the, for example, by the CAD software, and even you can just do that through doing some script. And after that, we have two different conditions. Initial conditions, for example, we are setting the temperature of the building in our simulation, in our next simulation, at 45 degrees centigrade. It means that the initial condition inside the building for the temperature, I mean, is 45. So initial condition, it means that the conditions actually exist at the initial time inside your computational domain. And then we have the boundary condition. It means that all conditions that we apply at the boundaries. So, for example, we are just considering a window, a cooler, and an open door in our computational domain. Then you need just to discretize your domain through the mesh and the grid generation. I will explain the meshing in the next slide. Don't worry, because we need just to discretize and divide our computational domain into very tiny and small cells. And after that, you need just to select the physical models based on your physics, and you need just to set some solution controls, for example, based on your equation, your simplified equation. So you can just select which scheme is suitable for discretization, and even what is the best time step for solving my problem. So you can just set the different criteria, and these all steps are categorized as a pre-processing. In the processing step or the solver, so you need just to select your solver. It's a single phase, it's a multi-phase, depends on your physics. And then you need just to solve the flow and monitoring the convergence. So yeah, actually the CFD is based on some iterative method after the discretizing the geometry and actually the equation. So it's the iterative method, and at each iteration we have a criterion. So you need just to meet that criterion, and based on that, so you need just to monitor the convergence. It's like a loop. And so once it meets the requirement, so you can just reach your final solution. And also you have the pre-processors. And the last one is just post-processing. Pre-processing, processing, and the last one is the post-processing. It means that your solution is complete, and now it's time just to visualize the geometry, the grid, and all of the variables, flow variables, heat variables, and you need just to interpret, evaluate all of the results as an expert. So when I actually say the mesh generation, it means that we need just to break down our geometry. So we need just to consider a geometry, create the geometry in the CAD file, in CAD software, or even in the your software, for example, in FDS, that we are doing that today through just doing some script. And after that, you need just to discretize the geometry, this, for example, box into the very small, tiny cells. So we have two different mesh. We have structure mesh and we have unstructured mesh. The structure mesh that you can see here, so it means that when you are looking at this mesh, so you can see that there is a not the uniform, there is a pattern, there is a specific and certain pattern in mesh generation. So actually the expert uses, for example, the hexahedral or the equilateral or the prism type of the set. It means that he selected just one specific pattern just to generate a mesh. But for the unstructured mesh, it means that we have no specific pattern just to generate the mesh. And also that you can see in the middle. And also if we combine these two mesh that is very common in engineering, so we can have the hybrid mesh. It means that, for example, this is a hydrofoil that you can see in these three figures. So we generated the structure mesh around the airfoil. So we need just to, the point of interest is actually this leading edge and this tailing. So we just created and generated the structure mesh around the airfoil. And for the areas far from this airfoil, so we generated the unstructured mesh. So, and also the other important parameter is just uniformity or non-uniformity. Here you can see that because the point of interest is around the airfoil, so we created a non-uniform mesh. It means that the mesh, the size of the mesh is very smaller than the size of the mesh for this area, because again, this area is the point of our interest. Even for this figure, so you can see that we have dense mesh around the object. So let me just give you more elaboration on the mesh on this simple example. So we have a box. So it's a 3D box. So it means that we have X, Y, and Z. The dimension is not our actually focus now, but consider is, for example, 1 by 1 by 1 meter. So we can't just solve all of those governing equations for this computational domain once. So it's an iterative method. It's like a sweeping. So we need just to divide the computational domain into the tiniest small, tiny and small steps. So for example, here the number of division is 10. It means that we have 10 equal and uniform cells at each direction. So the number of division in the X direction is actually defined by the I, in the Y direction is the J, and in the Z direction is actually defined by K. So for example, this box is divided by 1,000 cells, 10 by 10 by 10. So it means that we have divided it by 1,000 cells. Any questions so far on the meshing or the CFD? Okay, I think it's enough just to give you an overview regarding the CFD and meshing, because you need to know actually these concepts, because I'm gonna just use them in our script, and if you don't have any idea, you will get confused. So as I mentioned last session, last lecture, so we have different methods, different approaches to solve a numerical simulation. The first one is the commercial software. They have a license, copyright, and so you need just to buy and purchase the license. But they are visualized, they are very user-friendly, and they are very popular at the university, for example, in the academia, and even in the industry. The second one is just doing some code, and it means that you need just to develop or even start writing a code from scratch. So you need just to do that in the MATLAB or even the Python, Fortran, so it depends, or C, C++. And the last one is just open source. It means that you need just to provide some input. You can't see them visually. It means that you need just to do some commands. They are not code, they are just some script. To be honest, for the FDS, it's very straightforward. And don't worry, they are actually they are very easy. So you need just to know some commands, and through that, so you can write your input. This process, student, it means that it's pre-processing. And once you run this input, it's processing. And if you complete that, so the next step, I mean that the solution is complete, it means that the next step is the post-processing. So here I'm gonna just explain each of them in details in the next slide in the real example. So very quickly, you need just to start your script through the head and tail. The head specifies the job ID. The mesh defines the computational domains. Time actually sets the simulation end time. For example, you have a building, a specific building in your mind. and we have an origin of the fire. If you remember, we have different stages in the fire growth. For example, the initial stage, or for example, the flashover, pre-flashover, flashover, and just stable period, and then we have a decay. So you need just to study the behavior of fire for example, 5 seconds, 50 seconds, 500 seconds. So it depends on your need. You can just define the value of time through the surface yourself. So you can just define the properties of the surface. For example, I have a building, so I need just to specify the walls or even the fire. So only you can just define the properties of the surface. Obstacle. So when you have actually a building, so you have a different bedrooms. So you need just to consider some walls. So you can do that through the obstacles. Or if you have any vent, you have any opening, so you can use this command. If you have a reacting flow, if you have a fire, so you need just to consider the react as a very common command in the CFD and in the FDS. So it defines a chemical reaction for the fuel that we will study that later. And actually this one is just as a slice file. So if you are interested just to study the behavior of velocity, the behavior of temperature, the variation of the temperature at the specific cross section, for example, at the z is equal to, for example, 2 meters. So here you can just use specify this slice file, and in the post-processing after completing your solution, you can just use that. The device, you can just use this command just to set some devices, some like a sensor, like a water mist, like a sprinkler in your computational domain. And the next one is just the boundary files. So through that, you can request the boundary file for certain quantities. You can just record something. And the material, it means that you can just define the material properties assigned to the specific region. And the last one is the miscellaneous. It means that if you are just setting the temperature, ambient temperature inside the building, so you can use this command just to set your ambient temperature. So last week I told you how you can just download and install the FDS. Is free and you don't need any license. It's open source software. So if you have not completed your installations FDS, so please take your time and do that. Only follow the instruction on the screen. And meantime, if you have any question, please let me know. Just please do that and bring your laptop for our tutorial, this week tutorials. Ensure that you install that properly. So you can just open our lecture note on iLearn, or you can just Google it, just pull up your browser, for example, the Google Chrome, and just type the fire dynamic simulator and download. Click on the link for is specified by the nist.gov. Depends on your computer system. You can just select the Windows, Mac, or the Linux. I selected the Windows. Once you click on this option, this hyperlink, either in our lecture note or on the website. So the downloader starts to download. It's not very big. So once you complete your downloading, so you can just go to the downloads folder and run this installer file, this file, FDS 6.9.1 is the latest version. If you double click on that, maybe you face this message. So only you need just to select the more info and then run anyway. In case if you face this message, so you need just to authenticate with your identity provider. So you can just do that through the McQuery Hub. You need just to only log in with your McQuery ID, student ID. And once you complete it, you will see that it turns to the authenticated, and also you can see this green tick next to the authenticated. So in the process of installation, you will get asked yes, no, or quit. So you need just to type yes. If you do that, you need just to reboot your laptop or PC or the computer, but don't do that. Mostly it works, but after our session, definitely you need just to reboot your computer. Now you have the FDS on your laptop, your PC. If you go to the Start menu, if you find the FDS6 folder, so you can see that several options, several materials on there, and inside this folder. For example, we have the FDS, some technical reference, some user guide for the FDS. We have smoke view and user guide for the smoke view. But what is the smoke view? What is the FDS? FDS is our main solver, but for the post-processing, so we need a software to visualize that. For example, we have this process even for the OpenFOAM. OpenFOAM is another strong CFD software that is open source. For the open source, so yes, you need just to provide an input, doing some script, but you need another software just for the post-processing and visualize your results. This software is the smoke view here. So if you want to ensure that you install the FDS properly, so only you need just to type FDS. And if you see these details, if you see that the MPI version and these details, it means that you successfully installed FDS on your system. I give you 2 to 3 minutes just to complete your installation, and then we will start simulation this building. Okay, we have a message. Let me just have a look. Yeah, but actually Abacus is used generally for some the base. Let me just explain. So for the just CFD, we have three different approaches. The first one is the finite volume method. The second one is the finite element method. And the third one is the finite difference method. So depends on our physics, depends on our application, so we can just use them. So the base of the FDS is the finite volume method. But for the outputs, it should be, I think, it should be finite element method. So they have a different assumption in these three methods. So mostly, I can say, for example, for all cases, but mostly we use the finite volume method for the CFD, but you can see that a lot of papers, journal articles, they consider the finite element that are correct definitely. And the other one is the finite difference. The difference is only in their assumptions. Is it clear? No worries. And abacus actually generally is used for mostly in civil or the solid mechanic instead of the fluid mechanic. Okay, any questions so far? Please let me know. Okay, so I need all your attention here for this example. Just please pay attention to this example. Okay. So we have a building. We just simplify that. So we have a different walls here, different bedrooms, for example, and some bedroom actually have the door is open. For this one, for example, is closed. Depends on the different situation. I consider only this example. And so this one, I can just name the whole actually uh, shape as our geometry, our computational domain. So again, just please let me know if you have any problem with any of these definition. So I consider the downstairs as a mesh. Let me just write something here, point and pen. Yeah, I just named the downstairs. I mean that this black part as a mesh is the ID. And also I specified the name of the officers as a mesh O1, the red one. Okay. And also we consider we have a window, it's like a cooler, and the air velocity is 2.5. It's coming into the building. The window is open and the air temperature is around 4 centigrade. The ambient temperature inside the building is around the 45. You can just change that to the 25, depends on your assumptions. It's the 3D example. So we have X, Y, and Z. We have an open door in the upstairs. We have open doors even here. So you can see that the coordination of each section. So here it means that the first one represents the X value, Y value, and the Z value. But what is the meaning of this coordination? Let me just explain that. I should just change that to the pen. Okay. So in the Cartesian, we have x1, y1, and z1. But if we are just defining a geometry here, it means, sorry. So it means that we have minimum coordination here and maximum coordination here. So the format always is like this. Keep it in mind. X mean X max. Y mean Y max. Z mean and Z max. So here it means that it's a start from X mean. This one is X max. So here the X minimum X is 1. And it extends to the 2. We are just addressing the opposite corner. I mean that the min and max. And here you can see that we have the minimum y and the maximum y. So minimum and the maximum y is set at 0. And how about the height or the z coordination? So the minimum z is here, is considered as a 0.75 meter. And what is the top point for this window? Is the 2 meter. Please let me know. It's very important because you will get confused if you don't know the format of coordination in the FDS. All good? Okay. For example, if you are just defining this, I mean that the red wall, the wall 1, it means that this point is your minimum, and the opposite corner is the next point. So what is the x min? So for the wall 1, what is the minimum x? Is, for example, 4.4. Okay? Okay, we have a question. So yeah, all of them are meter. Okay, yeah, I will just Andy explain. Let me just first explain the window here. Andy, we need just to define the coordination of the window. So what is the minimum coordination? It should be here. What is the maximum? It should be the opposite corner here. Okay. So in the definition of window, so the coordination here is just like this. Is 1, okay, 0, and 0.75. What is the coordination of this point? Is 2.5 meter, 0, and 2 meter. So when we are just defining this section, this surface or anything, so we need just to follow this format. X min or minimum x, maximum x, minimum y, maximum y, minimum z, and maximum z. So it means that for the window, it should be 1 to 2.5. It means that the dimension in the x is starts around 1 and ends to 2.5. The y minimum and y maximum is 0. What is, how about the z? It should be 75 to 2 meter. And is it clear now or not? And if you are hearing me, just please let me know that is clear. Okay, yes, but how we know? No, the exact value are given. Don't worry. This figure that you can see is given. Don't worry about the values. But explain that maybe you get confused. What is this coordination? What is exactly presents? So it presents minimum x, maximum x, minimum y, maximum y, minimum z, maximum z. That's it. Don't worry. Okay. We will practice it again and again, and you will become familiar with this one. But still, whenever you have any problems, any questions, directly just please send me a message or even the chat box for the everyone. Maybe it's a question the other student. So the first step is just to starting and doing and completing our input file for the script. So we need just to start through the head, and we will finish that with height. So you need just to include this and symbol. So head CID. So I name this domain as an office. You can just name it as a, it's optional, as a building, anything that you like. So what is the simulation time? So I'm gonna just consider it for the 50 second, but depends on your need. For example, we can just reduce that to the 5. If we, for example, I think for this session, we have to just reduce the time because it takes a lot of time just for simulation. I will show you, but still it depends on your system configuration. So what is our initial condition, initial temperature? So we need just to use, let me just use this definition. They give you more details, and definitely you will find them helpful. So here you can just set the ambient temperature to the 45 because again, it's given by the question. It's not our assumptions. You can see and look at the figure. So the next line in your script is the mesh ID. If you remember, I told you, I consider the downstairs as a mesh and the upstairs as a mesh O1. You can just consider the different names. It's up to you. It's your choice. For example, you can name that as a mesh O1, mesh O2, anything that you like. But you need just to name it. So what is the next actually term in this line? It's a color. Sorry, it's a color or the RGB. So you can just define your color, your desired color, or even you can just use the standard colors like a red, blue, yellow. So it depends on your actually preference. So we consider the black one here as a mesh or the gray one. What is the next term? Is the IJK. If you remember, I told you, we have the 3 dimensions, X, Y, Z. The number of division in the X means I. The number of division in the Y direction is J, and the number of division, I mean that the mesh in the Z direction is defined by K. So when we say IJK, when we say IJK, it means that this only the downstairs, not upstairs. The downstairs is divided in 56 uniform cells in the X direction, 91 uniform and equal cells in the Y direction because it's larger than the X dimension, and is divided in 21 divisions or cells in the Z direction. Maybe the question in your mind is that how we can just define the number of the mesh. It depends on your knowledge. So you can just do that, and you it's a lot at the beginning for you, it's kind of the trial and error, but after a while you can just define a good estimation at the beginning. So you can start the number of the division or the meshing by looking at the dimension and what is the point of interest, and based on that, so you can just make decision. You will have a uniform or non-uniform, and regarding the number of the cells even. So again, the IJK shows the number of division in the X, Y, and Z direction. Sorry, we have some issues. Okay. Yeah. And what is the XP? XP again shows, and you can just define the minimum and the maximum coordination in each direction. So again, I define the downstairs as a mesh. I just consider the gray one as a color. I divided the downstairs geometry in 56, 91, and 21 uniform parts in the X, Y, and the Z direction. But the question is that how we can just define actually the coordination of the main geometry. Here you can just define that. If you have a look, so what is the X minimum? It's a zero. It's zero. This point shows the minimum coordination, and this point, let me just do some annotation here. This one is the minimum, and this one gives you the maximum. So what is the X minimum? It's a zero. What is the X max or the maximum X is 8. So I just put it 8. The next one is what is the minimum Y? 0. What is the maximum Y? Is 13. It's a longer length of the office. What is the height? The minimum height or the Z is 0. What is the maximum Z? Is 3. So I put it them here. And then you need just to close the line. You can start with this symbol and you can just close each line. Any questions so far or no? Please ask your question. I know that maybe at the beginning, initially, it looks a bit strange because you are familiar with the commercial software, but it's a bit different. It's open source, so you need just to do some script. So it means that it's clear to all of you. Okay. Let me just clean the screen. Okay. And also we define actually the bottom, and we need just to define the top part. So as I told you, I consider and name it as a mesh O1. I mean that the red part. I consider the color or the RGB. When you use the standard color, so here it should start with the color and it's equal to the, for example, red. What is the IJK? The number of division in this dimension, in Y dimension, and in the Z dimension is equal to 21, 21, and 14. Because it has equal X and Y dimension is 3 by 3 meter, but the height is 5 meters. So we consider just 21, 21, and 14. What is the dimension? How we can just define the mesh one as a geometry, as our computational domain. So what is the, you need just to consider this and this coordination. What is the minimum X? It's a 5. What is the maximum X? It's a 8. What is the minimum Y? Is a 10. What is the maximum Y? Is a 13. So 10 and 13. You need just to consider one decimal. What is the minimum Z? Is a 3. It's here, it's 3. What is the maximum height? Is 5. So it is 2 meter high. So now I just start and name my geometry as an office. I define the time of simulation. I apply the initial temperature. And now I just define the two different geometries or two different meshes. So what is the next step? I'm gonna, if I told you as a pre-processing, we need just to apply, just select our governing equation. Here, our governing equation is the conservation of mass, conservation of the momentum, energy, and the species. Because we don't have, this case, we don't have any fire. Only we have a building. Then the next example, I'm gonna just include the fire. So only we have three different governing equation: mass, momentum, and energy. So the next step is just applying the initial condition that I did. And the next part is the boundary condition. So it means that all the condition that you need just to apply at the boundaries. So the first one is just this window. I name the surface ID as a cooler. It's optional. What is the color? Again, it's optional. So here it gives you more details. What is the temp front? It shows the temperature for the coming flow. We consider that as a 4 degrees centigrade based on the given values. What is the next? What is the velocity? The air velocity is considered 2.5, but be mindful of this minus. Let me just remove that. So this minus shows that the flow is coming into the building. You need just to consider this minus. So now we define one of our boundary conditions. So what is the next? I'm gonna just actually define the first obstacle. What is the first obstacle? It's the wall 1. So I name it and I just define the ID as a wall 1, the obstacle ID. And again, the next part, the next term, you can just define the color or the coordination. So for example, the X speed that shows the coordination like the previous slide. So it's start the point, the minimum point is this one, and the maximum point for defining this surface is this one. So what is the minimum is 4.4, is 4.4 minimum X, and what is the actually maximum X is 4.5. Why is different? So the X is not the same for this point and that point. The difference, gentlemen and ladies, just pay attention. The difference between these two shows the wall thickness. So the wall thickness is given 0.1 meter. So this value, the difference between the minimum X and the maximum X gives the thickness. What is the minimum Y? It's 0, so you can see that is 0. What is the maximum Y? Is 13. Good. What is the minimum Z? 0. What is the maximum Z? Is 3. Okay. Regarding the color, it's up to you. I just consider that as a red color. And you need just to define this is new, so you need to know that what is the surface ID. It actually represents and defines the obstacle within the mesh. So you need just to define the properties and the materials, kind of. So inert, here we have the different options. For example, the inert indicates a non-reactive, non-emissive surface, typically used for wall, floors, and ceiling. And they do not have any interaction with the fire or smoke. But we have other types of surface ID that you can use them. For example, if you consider them as a burner, that we will just use them shortly just to just to build a fire, consider a fire in our building. So we need just to consider it as a burner. We have a question. Let me just check that. No, no, not at all, Andy. It's up to you. So it's only just helps us defining the RGB or the color, only shows, only actually help you just to visualize properly and professionally. It's completely optional. Okay, just close this one. Okay. So I consider the wall as an inert, and I define the name, I define the coordination, color, and even the surface ID. I should just remove all of the annotation. Okay, so in actually the red wall, I mean that the wall one, so we have an open door. So it means that we need just to create a hole in our wall and inside the building. So we define the wall one, but now on the wall one, we need just to define the hole. It acts like an open door. So the hole ID, again, you define the ID of the hole. So the whole wall one, it shows that this hole, this opening is only for the wall one. You don't need just to define the color because it's like an opening. And then the next one is the XP. What is the XP? Again, I don't want to just explain that again. It shows that this point and this point. So it's 4.4, 4.5 because the thickness of the wall. What is the minimum Y? 7. What is the maximum Y? 9. What is the minimum Z? 0. What is the maximum Z is 3. From this point to this point. And also, I don't want to just explain that in detail to save the time, but after just defining the wall one, now it's time to defining the wall two, I mean that the blue wall. So for the blue wall, so the starting point is here. So you can see that 0, 7, and 0. The end point or the actually opposite corner is this point. So you need just to consider your minimum value from this coordination and maximum value from this point. And again, on your wall, you have an opening for the hole. So you need just to define the hole ID is a hole for the wall 2. And what is the coordination? The coordination is like this. It starts from this point and to this point. So you can just define that here. So it shows that minimum, if I can just write it here, it should be better. Let me just do my best. Yeah, it should be here. Yeah, oops. It's not working. So I need just to, yeah, this one is the mean. This one is the max, minimum X, maximum X. Minimum Y, because minimum Y here, as you can see, is the 7. What is the maximum Y? It's a 7.1. Again, the difference between these two, I mean that these two values, 7 and 7.1, gives the wall thickness from this point to this point. But because for the wall one, the difference between the minimum X and the maximum X gives you the wall thickness. What is the Z? Minimum Z is 0. What is the maximum z is 3. Okay. And we need just to, after just defining, because let me just very quickly review what we have done. We actually created we set the initial condition. Then we created two meshes, the mesh and mesh O1 as a downstairs and upstairs. And then we consider two obstacles, and on each obstacles, I mean that the wall 1 and wall 2, we consider the two opening as the open doors. And then the next step is just, it's time to set the boundary condition of the upstairs. So we have open door here. What is the coordination? X1 represents the minimum x, x2 maximum x, y1 minimum x, y2 maximum x, z1 minimum z, and z2 maximum z. So vent door or vent ID considered as a door. You are familiar with the surface ID. We consider that as the open. And you need just to define the x. And also you need just to consider, we define the window, but you need just to consider that one as a vent. So what is the surface ID? The surface ID is not a predefined. So we already defined that as a cooler. So we just defined that the vent ID is window. What is the surface ID? The surface ID is a standard for the door. So we use the open, but here because it's not the open, it's not open to the atmospheric condition. Our window actually, we have like cooler. We have airflow with the temperature of 4 and with the velocity of 2.5. So it's not a normal condition. So we are applying the specific conditions. So we already defined that as a cooler, and now we are just calling that condition that we define. And so here again, we need just to define the coordination and the color. Any questions so far? Good. I told you that we can just create some cross section in our domain. It's totally up to you. It's not mandatory, but just for analyzing and interpreting your results, you need just to have some cross section of the different variables. For example, velocity, for example, the temperature, or the actually heat release rate. Anything else that you, for example, the number of the droplet, the size of the droplet when you have the water mist. So you can just do that through this command. Actually the slice, not sure where is my mouse. Okay, my pointer here. Okay, when you have actually the slice file quantity, so I name it as a temperature. And the next term you need just to define your vector is true or false. So I highly recommend you just to select the true, because when you just select the true, it means that it indicates that vector actually quantities associated with the scalar quantity that should be also recorded. Let me just give you an example. For example, if we are just recording and storing the data for the temperature, if we just select the true, it means that we can just have a direction and magnitude of the airflow even on this cross section. Hope you realize that. And the next one is the coordination of the plane or the cross section. So the PB is mandatory, but if you are just defining your cross section in the Z, I mean that this cross section. So what is the coordination? The Z is equal to, as you can see, 1.5 meter. Even you can just define some cross section in the X direction. So it's up to you. I define also a slice file or actually the plane cross section for the X. what is the value of the x? So the value of the x here is 6.5. So it should be in this direction. 6.5, it means that after the red wall. And you need just to use tail to actually finish your script. And that's it. So this is our second example. So what you need, just let me just take that one, scar. Okay. So you need just to follow this instruction. So you need just to go to your C, drive C. If you have any questions so far, let me know. Otherwise, I'm gonna just implement all of these instructions. Okay. So you need just to find the installation directory. You need just to go to the program files and find the fire models. Go to the FDS and find the examples. Go to the fires and select one of the file, for example, the coach. So you need just to go, for example, to your desktop or anywhere would you like. I name it as, for example, CIVL. That's it. And I paste it here. Then you can just rename it as a office. And we need just to change the contents. So you can just open it with Notepad file. So you can see that there are some description. So what is the head is here is a coach, but we're gonna just totally change it. How you can do that? Go to the first slides here, I mean, and copy the text from here. And just remove all of the data and all of the inputs and just insert our script. Go to the next one and copy that and paste it here. And then you need just to go here, copy that and insert that here. You don't need just to do that from scratch. I provided it for you. And then you need just to copy these 3 lines and paste them with blank and just remove these blanks. Yep, one is okay. And here, okay, good. We need just to define our boundary condition here that we already discussed that. Good. And this one. Copy that as a slice file. And the text is like this. So you need just to save it, close it, and open your FDS. If you type the CMD, so you can just open the CMD comes with the FDS. You need just to type CD space, go to the folder. So yeah, copy the address and only right click here. It appears and it pops up and enter. So now you change your current directory for running. So you can use the FDS. What is the name? Office dot FDS, sorry, FDS file. So it used one process, but if you're gonna just accelerate that, we just divide our configuration in two different parts. So based on the number of the mesh, we can use the different process. So we have two meshes, so we can just define the number of the process through two. So only you can just FDS underscore local dash P number of the mesh or processes and the name of the FDS file that I showed you here. So instead of FDS, so you can just change that to the local dash P is the processes and number two. You need just to press enter, so you can just cancel it. It starts to run. Here you can see that the time step here, simulation time. If you remember, our simulation time was set to the 50. And I'm gonna use two processes because we have two number of the mesh. And definitely it takes a lot of time. So whenever you want just to finish that, you can just press Ctrl C. So it takes time. Even you can just close the window. It's up to you. I have already actually run this simulation and I will show you the results. So it takes time. Yeah. Yes, it asks you just to terminate the batch job. You say yes. I have already the results. So because we completed the pre-processing, we complete the processing, and I have already completed the processing step, the solver, and then last one is the post-processing. So I'm gonna go to this address, the without the fire, copy that, again, CD space, right click. So I have completed that. Just to visualize that, as I told you, you need just to type smoke view, okay, space. What is the name? It's the office dot smoke SMV. What is the SMV? SMV file is this file. So you need just to press the enter. Now you can see that successfully we model and run our simulation. There is the window, wall one, wall two, two opening, and one open door in the upstairs. So I'm gonna just looking at the results. So I can go to the slides. If you remember, I create a cross section at the specific Z. So I'm gonna just look at the variation of the temperature over this surface. So here you can see that the temperature of the cooler, the window was set at 40 degrees centigrade. The ambient temperature was set at the 45. So the red color shows the maximum temperature and the blue one shows the minimum temperature. So you can see that over the 50 second, even you can just extend that over the 50 seconds. So we have the variation of the temperature in this on this plane and in this direction. Now I can just look at the, for example, the variation of the this direction is a y, so we can just v velocity at the z equal to the 1.5. So here you can see that the variation of the velocity, actually the negative value shows that the reverse flow, and the maximum is the 2.5, that is the velocity of cooler. Even you can just look at the different parameters such as the u velocity. It means that the velocity in the x direction, v velocity in the y direction, and Also, you can just W velocity represents the Z, the velocity in the Z direction. So even we can just unload all of the data and we can just show the geometry that we did, show all. So you can see that there is a ceiling there. And also you can just press for the label, go to the label and show all. Here you can see that the different details about our mesh, even the dimension of our mesh. So you can just rotate it and look at that. Also, you can just go to the geometry. You can just look at the grid. Oh, it's not working. Okay, grid and grid, show grid. So here you can see the grid on this surface. So you can go to the geometry again, grid, and for example, you can say that show that on the grid location or show all. So here you can see the number of division. So if you remember, we divided the X, Y, and Z direction for the downstairs and upstairs in the different number of divisions. So any questions so far? You don't need just to do any script, don't worry. All are provided actually, all materials that you need are provided in the lecture note. Only you need just to copy one FTS example from the example folder, paste that in your folder, and then open the FTS file, remove the previous content, and copy paste all of the command that I provided for you. Okay, and if we want to consider, so only in the previous example, in the activity 2, we don't have any fire. So, but if I'm looking for the case of the fire, so it's activity 3. So I consider the location of the fire here. So you can see that I consider we have a fire with the specific properties that we will define that very quickly. And so we're gonna just analyze the amount of the soot and the heat release rate. So here you can see that the fire source HRR, it means that the heat release rate. So it's considered as a 1000. And so the location is considered here. Okay. So only to the previous input, previous script, you need just to include these commands at the end of that. So it's like what is the React ID? I name it as a methane. And here you can just provide some comments on the reaction. It's not very important. What is the fuel? It's a methane. So it's already is built-in material in the in FDS. What is the actually value of the yielded CO? So we can consider that as a 0.1, but what is its meaning? It means that from 1 kilogram fuel, so we have 1% of that as a CO, and for the value and amount of the soot, we consider that as a 5% in the 1 kilogram fuel. So you need just to define them. If your question is that how you're gonna just realize the exact value, it needs some fire and some combustion knowledge, but you are given in the example. But if you are interested, you just define this percentage. You need just to study some combustion resources. And after just defining the reaction ID, that you define some properties, now it's just time to define where is the surface ID. So the surface ID, we named that as a methane burner. The color is red, not important. What is the actually heat release rate per unit area is the 1000. We can just define that as an obstacle. So the obstacle ID is a methane burner. What is the X? So we can just define the X minimum and the X maximum, Y minimum, Y maximum, Z minimum, and Z maximum. And what is the surface ID? It's not the predefined or the built-in types in software. the software. So we just already defined that as a methane burner here. So we call that here. That's it. Here I just provide some details. So I'm gonna just add these commands to the fire. So let me just, you can just do that by yourself just to save the time with fire without a water mist. So it's this file. Let me just show you. It's exactly like the previous one. We only consider, for example, the case of the fire, the methane burner, and the obstacle. That's it only, and then reacting item. So let me just show you the results as a we completed the pre-processing. I have already completed the processing, and now it's time just to changing the address. Okay, good. And again, smoke view office SMV. Let's look at that file. So it should be in this direction. So I'm gonna just, if you remember, we don't have any option regarding the 3D smoke because we didn't have any fire, but when we add the fire, so we have these options. Now you can see that the density of soot, and you can see that just because of this window and this open door, we have this actually circulation of the air. Even you can just add the heat release rate. You can just, like the previous one, look at the temperature. So you can just define the different options. So now you can see that the behavior of the fire after the 50 seconds. So now you can just interpret what is the best action, what do you need exactly as a fire extinguisher, as a actually a sprinkler, suppression system sprinklers, just to quench and just to put off the fire. So I think it's enough for today, and let's call it a day. We will discuss, actually, let me just open that one. Yeah, we can just stop it. Okay, yeah, we can just discuss more details. We can just provide on more examples in your tutorial. Please attend your tutorial, and we can just work on this example with the different coordination and with the different boundary condition and initial condition. If we will get a chance, definitely we will work on this case exactly with installing the water mist above the fire source. Hope you have found this actually session helpful. Please let me know if you have any question. Otherwise, just take care. See you soon on Wednesday. No worries, Radal. Take care. Have a good night. Have a good day. Sorry.
Thank you.
No worries. Take care. No worries. Salman. See you.
Have a good day, sir.
No worries. No worries. Take care. Bye bye. Okay. See you guys. See you. Bye bye.